Hello everyone, I'm Yuanzheng Ci. This is the presentation for our ICCV paper, titled Evolving Search Space for Neural Architecture Search. There are a lot of modules or operations we can use in a neural network, and for the existing NAS pipeline, we have a human expert selecting useful operations from operations in the wild. The total number of distinct operations is usually limited to less than 10. Actually, the search space we use evolves and improves as time goes by. As expert modifies the search space, making it smaller in size, the random search efficiency for that space is as well improved. But such kind of search space selection does rely on human knowledge, which is not always available or optimal. So, can we construct a huge and messy search space, which is also a superset of our dedicatedly designed space, then obtain a superior, or at least equivalent result from it? This is actually a less discussed problem in recent NAS literature. So we set up a search space with 27 distinct operations and tested several reasonably fast NAS algorithms. It turned out that they either failed or performed poorly in this setting. Aiming at this problem, in this paper, we propose to iteratively evolve the search space instead of directly search over the whole set of available operations. We start with a search space subset, which is a reasonably sized random subset of the search space pool. Then, in the next step, we gradually synthesize this subset by maintaining a fitness indicator for each operation. We update this indicator as we do SuperNet training, and prune the ones with its fitness indicator below a certain threshold. After that, we randomly sample some architectures and evaluate them with SuperNet weight. We aggregate the operations that appear in models with the best accuracy-cost trade-off to get our final optimized search space in this iteration. Those green dot models used for aggregation are as well considered as intermediate search results, or the final results if this is the last search iteration. Otherwise, we will replenish the search space with operations sampled from the rest of the operations in the search space pool, and then go back to step 2. We iteratively repeat step 2, 3, and 4 until the stop condition is met. As long as we can assure the optimized space is continuously improved, we can always inherit the last optimized space with more unseen operations, even beyond the current search pool. We name this scheme as Neural Search Space Evolution. For the search space, we constructed a 27-operation space for our experiments, which has more than 10 orders of magnitude more possible architectures than the compared setting in single-branch scheme. We also proposed a probabilistic modeling for multi-branch modules, which allow us to further increase the size of the search space to more than 90 orders of magnitude larger than the compared setting. Yet the performance distribution of random architectures within this large space is worse than that of its cherry-picked 9-OP's counterpart, which consists of commonly used depth-wise convolution modules. In the mobile setting, our result over 27-OP space outperforms previous regular space methods by a large margin. By inheriting the final optimized space from 27-OP's pool, we resumed the search with additional OPs used in ImageNet and was able to improve the result further. This result is also compared to ImageNet in the next figure, with our result achieving better performance. Here, we analyze the performance distribution for architectures within the final optimized space in each round. In our experiments, it takes 6 rounds to traverse 27-OP space, and the quality of the optimized space in each round, as shown in the figures, demonstrate a continuous trend of improvement. The same trend is observed for the best fully evaluated intermediate results as well. For the intermediate space within an iteration, we show that both search space simplification and aggregation improves the space quality by a considerable margin. This is all about our paper. With our NSE scheme, we achieve state-of-the-art performance while minimizing the necessity of search space engineering. Please check out our QR code to get the code for this project. Thank you for listening.